Cool. Any question on the homework? I assume not. It's due on Friday, so do it as soon as possible. For project, any question on it? Next Wednesday we will be doing the pitch. So if you want to discuss, just book a time, and you should also look for your group partners to think about it. So the project can be either building a new AI music tool, so things like what we done in the homework, or exploring creative and artistic use of AI tools. So Moises itself counts, but think about how it can, how different basic AI models can be used in your creative process. So you could definitely get some idea from working on homework 5 to look into how people are using different AI tools in their music creative process. Cool. Other than that, any questions on the project? Nope. I guess just start thinking about it as soon as possible. Cool. So for the project pitch, just a short presentation should work. So these are stuff you can find on the slides posted on the website. Cool. So we should get started. There's still a lot of stuff we should cover. So last week we talked about AI song context. So if you work on homework 5, you get a sense of what it is. But basically it's an annual international competition to see how you can use AI in different perspective, different process, different perspective, different parts of your songwriting process. And they focus more on how human and AI collaborate rather than, it's like a single shot model. Sometimes, those models are still single shot. You just click and then you get something, but, just through curating or, improvising with it, or, even sending the output results to some other models to get, more interesting results. Think about how the AI process is like, human AI process. So we look at this very cool examples, which is a perfect examples of, when culture meets AI music, where, some of the symbolic music models, as we will see later, is that, it's highly biased toward the Western music notations and music standards. But, through just doing audio-based AI, they can do just like doing some sort of like F0 estimation, or, doing tone transfer, as we talked about a few weeks ago. Then, you can preserve that unique sounding or unique tuning system for the Thai culture here, the P9 tunings. And we look at a more recent sample, which is the 2023 winner. And you can see that they challenge themselves to use AI in every single stage. So you can definitely see how different part of it, the ideation would be, it's like grabbing stuff from Spotify API to sort of get a sense what are, things that could be more popular, to get some idea, and then use ChatGPT, Llama. I guess this is the earlier version of Gemini, to sort of get the idea, and then you can use ChatGPT to get the lyrics and blah, blah, blah. Then, composition, there are tons of different models that could do it. You can synthesize the vocals, and then you do mastering. This is also sort of AI based. And then even the visual and how you get a video clip is based on some AI video or image generation model. So, the goal here is for them is to use AI in every step of the production process. both for music, but also for the the video clip. So all different stage. Sometimes AI could be very helpful, especially this was back in 2022, 2020. So some of them AI is more useful than others. Some of them are really hard to use AI. Cool. We will just skip those. Oops. Cool. And last week we talked about no, not last week. Monday we talked about on how we can start looking into symbolic music generation. But the key is that when we talk about music generation or some of the AI music, people mostly are referring to these models that can generate music to some extent, either from scratch or conditioned on some other inputs. But the idea is that there are two main paradigms, which is like, do you want to generate sheet music that you can later synthesize into audio, or you want to generate the waveform, the mixture, or the actual sound that you hear directly. So for symbolic music, we will be talking about MIDI. Today we will finish it, but we will also look into Pianoroll-based model, which is more like the computer vision image generation like approach. For audio, there are you can directly generate a waveform, or you can do spectrogram. And nowadays we have latent spacing, so that will be the last topic, which is more relevant and more current. On all the models that you heard, Suno, whatever model, mostly those with waveform, based audio domain based music generation system are using latent diffusion-ish model. Cool. I will skip this. So today we will keep talking about how you can use more language-based or text-based, models, which share with natural language modeling, like natural language processing models, like RNNs, LSTM, and Transformer. So last week we talked about some of these, looking into what language model is, basically just, looking at the probability and what we want to increase some of the, most likely next word given the past sentence. And then we can do generation. So the key here is to design a machine learning readable music language. So we look at the first example, which is ABC notation, which is pretty simple. So, basically just, represent each note by some letters. So, with this, we can basically train this model. This is the first model we look into. So, Folk RNN, which is an RNN, recurrent neural network, to generate those ABC letters. So, this you can think about this as a early version of what we are looking into today in ChatGPT. So ChatGPT-ish model are usually using a transformer, but recurrent neural network is sort of like the transformer 1.0 or 0.0 that people were using 10 years ago, maybe 5 years ago. So basically those are neural networks that have loops. So the key is that there's a memory going through, and the goal is to combine the memory and the input to make prediction. And that's why we want this loop. And that loop basically means that there are some information passing from the past to the future. So we look at vanilla. We will just skip these. But last week we talked about this LSTM models. We won't go into details. Even though it's not so complex as transformer is, but implementation wise, it could still take some time. But the high level idea to see how LSTM work is that there is sort of like a highway on the top, which is the long-term memory module that just pass through all the cells, each single state that will pass from the past information to future. And your key is to sort of like update these long-term memory module, but also grab information from that to compute your output. So first you want to decide whether you want to erase the stored memory. And then you want to see if you want to update the memory based on the input that you have at the current time step. And finally, to get the current output, you want to see how you can combine the memory that's stored in the memory system with the current input. So that's pretty much what LSTM is. So, on a very high level, so these are, some of the names of those gates. But basically there are 3 gates in LSTMs. Cool. And we talk about why it's very hard to train LSTM. And that's also part of the reason why nowadays people are doing more transformer models. Cool. I think that's sweet. We stop somewhere here. So, we look into word level RNNs and character level RNNs. So in this case, we are doing ABC notation. So, as far as you remember, these are these are some representing something like this. So it makes more sense to generate each single character or letter one by the time rather than, what the C2EG mean and, C2CG means. So that's the difference between character-based RNN versus word-based RNN. For character-based LSTM or RNN, we are generating each single letter at a time. Cool. Cool. So today we'll be, extending that to see how we can do better, more expressive music rather than, just single line ABC music that's, monotonic tunes only and, very limited expressiveness. Cool. So I assume you likely have some idea what MIDI is, but MIDI, even though people use MIDI in different scenario, but MIDI itself technically is a communication protocol between devices. So it's just defining how these different hardware device talk to one another so that they are sharing the same language. And if you look at the IO, it's just 5 pin. So for today's standard, it's a very old, analog. It's not analog. Very old digital communication protocol. It's just 5 bit of information in some sense. So in MIDI, if you have some idea, basically MIDI is to control how you play and music instrument rather than the actual sheet music. So that's the key difference between MIDI from some other format like music XML or some Lili-Pon format that's specific for sheet music or music notation. So in MIDI, you will look into some sort of like note down, which define when to start that note, physically defining how to control that specific instrument, and note off and delta time means that how long you should wait until the next event. Program change will set the instrument. So technically is that your instrument has different programs, different instrument, different sounds built in. What's is called a program inside the instrument. So that program change will switch from different instrument or different sounds that you have. And there are also control change. It's defined by your own device. But one thing interesting is the pitch bend change, which is very common on some of the MIDI keyboard. At the lab, you will see that wheel that you can, bend the pitch so that you create, glissando or any thing that's continuous in pitch. Cool. So we won't look into detail on MIDI. Most likely, we are just using note on, note off, delta time, sort of get the duration and also program change to see the instrument. Other information could be useful, but most likely it's very hard to use them because they are not generally being used in all the MIDI files. So, MIDI note numbers, few people actually will go on and remember all these numbers, but usually what you need is that middle C is 60. That's it. And then, it ranges from 0 to 127. So it's, technically wider than the standard piano pitch range because, standard piano only has 88 keys. So it actually goes below the lowest key on a piano and also go beyond the highest key on the piano. But anyway, middle C is 60. That's all you need to know. And even though it's defined in MIDI nowadays, pretty much whenever you see a number representing a note, then it's more likely, MIDI note. Cool. So we can do, represent music in some sort of like MIDI message. So this is what a MIDI file would look like when you represent something like this. So, what it works is that you have like note down 67. So you sort of like define the instrument, your keyboard, to turn on that note. So it will generate, some sounds with that specific pitch. So, 67, which correspond to, the G note here. And then you define, so MIDI, it's a very old protocol. So time shift quarter note is sort of like the delta time event in MIDI message. So basically it says that, well, just wait for a specific amount of time. So in MIDI file, you can specify how long you wait, but, technically we can view it as, just wait or, shift your time or shift your time cursor, to some other point. So you will wait for a quarter note, and then now you turn off the note, and at the same time, you turn on another new note. So, you can just keep going on with this idea that, just, get all the notes. So, immediately you can see that how this could use to, represent polyphonic music. Because, basically you can just do two notes on at the same time. So when you have like two notes on at the same time, it would just turn on two notes at the same time. And then, now you time shift so that you move eighth note here. So now your time shift is shorter because now you just wait for an F note to go to the next pair of chords. And then you have another pair of notes. And then now you shift to the next onset. This time is half notes because there are 4, 16. Wait, is it half note? Yes, it's half note because there are 4 eighth notes. And then you turn off those notes. And you just keep going on, and then you turn on these new nodes, and then you just shift to the other position so that you can turn off these two nodes again. So that's how MIDI define polyphonic music in a very technical specific way. So think about MIDI rather than defining what each note is and what the duration is. MIDI doesn't work like that. MIDI is more like how you physically or mechanically controlling the music keyboard. So that's the key. But anyway, with this message, you can sort of get a sense that you can use ChatGPT ish model to generate these message. So go on for given all these things, what would be the most likely next message to come? And that sort of define whether you want to turn off this nodes or turn off some of the existing nodes or create or turn on a new node. So this is like back in 27, even though the paper was out at 2020, so a bit confusing. So 2017, which is one of the very first model that actually look into the full potential of MIDI. So the key here is that they are actually leveraging the velocity information in MIDI. So some of the past work, they also work on MIDI generation, but they seldomly look at the velocity part. So that's play something, back in 2017. Um, Hopefully it works. And it doesn't. Let me see. Oops. Um, well, doesn't recognize voice. Oh, let me restart it. About examples. So, not too bad. So back in 2017, when people are starting looking into some of these models, so this was trend on this very cool data set is Yamaha piano competition data set, which is more commonly known as, Maestro. So it's basically something like the piano we have here. So, player piano, or not player piano is like a piano that you can record the very fine grained MIDI message. So they just do this. So Yamaha just do this competition annually, and they will invite musicians to compete, and they will give you grand prizes, and the winner gets some prizes, but at the same time they will collect data from your playing. So that's the downside, but if you like, you can join. But anyway, they have this competition data set, so those are very great performance on piano, and you have the MIDI files, but you also have the audio. So in some of the later work, you will see how you can actually use it to approach transcription model, going from audio back to MIDI, but also synthesis model going from MIDI to audio. But in this case, how we can generate those very expressive MIDI data, where you have very expressive timing, but also very expressive dynamic. And that's what you just heard. Um, one more, I guess. Usually you will hear something very familiar at the beginning. That's because these model usually we won't use it just from scratch. Usually we will we call it prime melody. So think about it like a ChatGPT prompt. So you will just give some initial material so that the model can improvise from. And at the end of the day, you can remove those prompt, or you can keep it. But generally, the model work much better when you have something to extend rather than just generating stuff from scratch. So if you like, you can actually play with it. So this is like an experiment with Google. This is AI duet, but basically that's sort of part of the model they are using in performance RM. I think this is much simpler model. Anyway, there will be some model reacting to what you get. Whatever, I don't know what I'm playing here because it's on the keyboard. But anyway, if you have any sense, you can play it, and you can actually also connect to MIDI keyboard to better on keyboard. But anyway, you can play it, and the model, as you will see, it would usually just follow what you some of the patterns that you give to prompt it. But anyway, this is AI duet. It's based on some similar model performance RN in usually a much early version. Cool. We won't watch it, I guess. Cool. So a much more modern architecture called transformer, but train on the same model. And if you look at the representation, basically the same. So basically you are using the same models, same data set, and same setup, how you represent the music, but we can listen to some of the more modern model, how to generate the music in the same data set. Cool. Just abruptly stop. Anyway, this is transformer. We will talk about what it is later. But it's a demo. So this is like continuation. Anyway, you get a sense. You can definitely see some, overfitting or signs of that the model does just remember this song. But anyway, in general, the model still generates something interesting. So almost the same representation as performance RM, just that now we are using transformer. So in the next few slides, hopefully, transformer is you likely hear it at one place and other. This is sort of like the one of the most important model, other than CNNs in deep learning. So in the next few slides, we will dig into what a transformer is, and hopefully that will give you something that's reusable in the future, and hopefully transformer stays for several years more. There's a chance that maybe next year people won't be talking about transformer. So that happens. So like for LCM, for some of the model, at some point, these models just evolve and there will be better model coming up. So transformer is a very important model that's being proposed in 2017. So it's a type of neural network that use the self-attention mechanism. So, the key to understand transformer is to look at how this works. So that is the original, actually not the original, but I try to simplify it a bit. So transformer originally is proposed for machine translation. So going from English to German, English to French, or whatever, languages to another language. So that's what the original transformer is for. But this is sort of like the adaptive version, how people are using it for generation tasks today. Cool. And so the key of transformer is the self-attention. Everything else you should be pretty familiar with, kind of. So, everything else is just some, add and normalization feed forward. That's, just pretty simple, dense, fully connected neural network that we see at the very first that, just 10 nodes, and you just compute all of them, do some metric computation, and you do it again and again. And so same for linear, and you see softmax. So basically, the input would be all the previous words and you want to see what the next word is. And by doing softmax, you are sort of like predicting over the whole vocabulary. So think about, a model that could potentially have, say, MIDI generation. There are 128 pitch. Then you want to see what are the probability to get each single different note. So, we will look into what self-attention is. But, the key concept of self-attention is that, when we are doing this language model, lean think, what we want to do essentially is to generate the next word given all the past information. But you can think about, what your model is doing is that, when you are generating the next word, what should you look at in all of the past information? So, in this case, just look at all different words in the past, which is what we call a uniform attention. But it doesn't make much sense because, if you have a very long article or, a long sentence, there's just different ways on how these words have the inference onto the notes, the word that you are generating next. So in this particular case, we will likely say agree that transformer is the most important word to get what this question mark is. A transformer is something, so that something should mostly depends on transformer, and the model should look at transformer and see what would be that specific word. So and is and pretty much everything else is just looking at is it singular or plural. So tiny bit of information, but most information should depends on that. So this is the key idea of transformer, is that we want to have variable attention, and that should depends on the the input. So transformers are basically models that learn what to attend to from big data. So in the next few slides, warning is that it's very challenged to understand transformer, but I would try my best to sort of give you an idea what transformer is doing in the very ground level. And the whole system is just doing this again and again. That's what deep learning is. You define a very simple matrix computation, define a very simple math computation, and then you do it, hundreds of times to build all the layers, or do it again and again, and then you train it with some model, train it with some loss function. Cool. So what we do in transformer, these are the complexity of it. So for each single word, first what we would do is we will use the matrix to turn them into some of the vectors. So these words for the model is just some number. So it doesn't have any meaning at the beginning. These are just maybe 1, 2, 3, 4, or 99, 81, 76, 62, whatever those numbers are. The model never know what this word is at the beginning of the training. So what the model would do is that there will be 3 metrics just looking into these or different words, and it will turn it into 3 different vector. And these vectors are learnable, that the model should try to optimize these vectors. So what it does is that when we are generating the next word, the model should sort of like combine all the information in the past to generate what the next word is. So how it does is that looking at the very last word that we have, so going to the question mark, what we have is the last 4 words that we have. So for each of them, we will compute something we call the key vector, and based on the very last word, we will have the query vector. So what we does is just doing modification or inner product. So use this key and use it as sort of like a a thing that we want to check how does the query vector match to that. And so use this query to check with to see whether this is something that we are interested in. And you can also check it with transformer, check it with is, check it with itself. So you sort of get a relative attention. So initially, these will be something that initially these will be some value that doesn't have have any sense of what are the more important words. But after the training, the model will learn to assign different weights to these different words. But anyway, here are all the attention score. So I think there are something missing here. Let me see what I have. Anyway, so the goal, you have to do some memorization here so that all the attention score sums to 1. It doesn't look like what we had previously, but anyway, so all these attention score will sum to 1. That's the numeration thing. What you want to do is that using these value vector, so now you do a weighted sum of them. So, take the weighted vector. So this is where the self-attention is working hard, that, you just combine all the previous information with different weights, and then you sort of use it to get the prediction, so that you use the prediction to guess what the next word is. So this is the full, self-attention mechanism. Don't worry too much if you couldn't parse it at the first sight. But what you see is that, what you have is to first determine what's the attention. So the weight to look at all different previous words. So you get these attention score that determine which word is more important than the others. So in this case, transformer would be the more important word. Now you know how to attend to these words. Then you grab the actual information from those words and times it, or take a weighted sum based on the attention score with the actual value, so that you get the prediction. So that's the key. And if you look at the original paper and the transformer model, looks something like this. Super hard to parse, but that's the key. Questions? Nope. Cool. Anyway, just to get a sense what transformer is doing, on a high level, what it's trying to do is to see what words are more important than the other, but still we want to aggregate all the past information to it. So why attention mechanism? What it essentially wants it to do is something like this. So, this is the very first paper that talk about self-attention. So looking at the FBI is chasing the criminal on the run. So the red word would be the word that you are generating. So when you start with the next word FBI, it will look at and then when you are looking at the next word is, then it will look at FBI. And then now you look at the verb where you are generating the word chasing, it will look at FBI and is, because you need to know what the subject is, and then whether it is, singular or plural. And then, think about something interesting would be, looking at criminal. When you are generating criminal, it will look at chasing. So none of these together. So, criminal associated with chasing. And then, looking at the round, it will attend to FBI, chasing, and criminal. So that's sort of the idea. This model will learn dynamically to attend to different previous words. And, originally, this is what we call self-attention. So, determine how how we should pay attention to all the past information. But originally, attention was not proposed just for generation. It was originally proposed to do translation. So looking at this example, what we want to do is likely French to English, but there's a chance it's English to France. But I think it's French to English translation. So at the y-axis we have the French. And on the x-axis, we have the English. So if you look at the attention, think even we are doing this translation, you will see that, European Economic Area, it will translate to, zone. I don't know how to pronounce it, but, it's just the opposite way, because that's how French work. So zone, economic, European, sort of something like that in a different order. And you will see that it's just a different shape of that attention matrix, because European will attend to the last word here, but area will be attended to the zone. So that's what the attention mechanism is doing in machine translation. When you are translating a sentence, whenever you are generating the next word, you are looking at different words in your original sentence. And using transformer for text generation or natural language generation, it's just using this idea cleverly all the past words that you have. So what are some of the words that's more important than the other to look at? Questions on this? Cool. So these are natural language. Who cares? Well, we care. We care. ChatGPT stuff like that. Those are models using these under the hood. But anyway, we're talking about music. So we can look into how attention work for music transformer. So this is a particular model when we are using transformer to generate music, as you just heard, the very nice audio example. But if you visualize the musical self-attention, so there are also some complexity on attention is that, usually we don't compute one single attention at a time because, attention is something that just sums to one. So at the time, you can just look at one single thing. But that doesn't work in general. If you think about it, it's like, well, there could be multiple things. Sometimes we want to look at the chords. Sometimes we want to look at the rhythm. Sometimes we want to look at different aspects of the thing that we want to look at. So usually we have multiple attention head. So which in this case are the different colors. So, some of the attention head will look at, first chord. Some of the attention head we're looking into the current chord. And, the pink one will be, when we are doing this very frequent pitches, it will looking into what are some of the previous rhythm so that it will generate something similar. So, this is like music self-attention. We can see a very nice animation. Oops. About that. That's my laptop's noise. Anyway, you get a sense what these models are doing under the hood. It will just look at different nodes in the past to generate when you are generating the next node. Question on this? No questions? Sorry, what?
It's a really cool visualization.
Yeah. It's actually itself a paper. Just visualizing it. So that's how Google Magenta does things. They have it's actually a HCI team rather than just a music generation team. So they just explore how you can use machine learning to generate music, but at the same time, they also look into how you can find a great interface to improvise. And they have like many much follow-up work on this to think about how human can actually interact with this model to guide it or to navigate through what you can get. But you can also see that the attention head is not so simple as you might imagine. Is that look at the yellow thing here. It's sort of like looking into some of these stuff, but later at the stage we're looking at something else. So it's very hard to actually look into what these models are actually attending to at each single time point. But in general, that's what transformer is doing, dynamically determining what are the most important nodes in the past sequence, long sequence of words, long sequence of nodes to look at. So think about ChatGPT is pretty much the same. ChatGPT is like 1496 token length or word length. So it's generating something very long. So when it's generating the next word, it doesn't make much sense if you just look at all the past words that you just generated. But more of think about a way to figure out what are some of the important information, say the subject, the topic of the whole article. You want to grab that, but some of the other details you don't want to look at it. So that's sort of the long-term self-attention is about. When you are generating these, you will look into some of the very recent history, but you will also sort of like always looking into the first base note that sort of determine the key of or the first chord being played. So that sort of define the key of your model. So at the end you will look at it and always looking at the first note that you are generating. It's actually always there. You are always looking at the last note, but at the same time you look at some of more recent history, but some distant past. Cool. So that's music transformer. And it go beyond just solo music. So what you heard is, because we have very nice data in piano music. So, you can generate very nice piano music, but MIDI is very interesting because it does have this MIDI program change message, which we talk a little bit about. But again, MIDI change, the reason why it's called MIDI program change is that it's a communication protocol. It's defining how this keyboard, how these keyboards should interpret this message to control the internal, sound engine to generate the sound rather than, human interpretable. But anyway, these MIDI program actually correspond to 128 sort of instruments. Sometimes it's very confusing. So looking at, the first category, these are piano and so you have different piano. And sometimes it's like electric piano 1, electric piano 2. So both are electric piano, but it's sort of like left for the the keyboard to determine what's the difference. But most likely it's using acoustic grand piano, but you can also have different version of it. But some of the other instruments, it's actually grouped into 8 instrument each for each instrument family. So you also have organ, bass, ensemble. These are multiple instruments at the same time, which is also confusing. But it's nice if you want to just get the more richer sound. And this would be, what's this? Percussion, like pitched percussion. You have guitar, strings, and at the end you will also have something that's very mysterious. I think there is a category called sound effects where you have gunshot sounds, clapping sounds that doesn't have any idea how does it being translated into based on each different keyboard. You couldn't expect what you're getting. But that's MIDI. So you can pretty much represent multiple instruments. So some of the past model, they also look into how you can generate music in that sense. So in this MuseNet is one of the very early version of how you can generate multi-track. So it's also using the transformer model, but now you actually change the representation. Somehow you try to instill or put the information of the instrument into that generation process. So this is different from MIDI representation, but rather it's actually doing this what we call compound word, where you just put instrument, velocity, and pitch at the same time and pretended that it's a new word itself, rather than generating the pitch and then time shift and then close the pitch. So this is one of the example generate music piece. It's not Bach, apparently. anyway, you can generate multiple instrument, and if you look at the representation, it's sort of like define what the composer is, who the composer is, and then what is the ensemble. In this case, piano strings, and then you just start the song, get the tempo, and then you just start getting all these notes. So piano using velocity 72, and then that's G1, and then you generate a chord, piano, 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 violin. That's the first chord. Actually, it's a very large chord. So 1, 2, 3, 4, 5, 6, 7, 8. So you have like 8 chords, 8-note chords, and then you wait for 12, say second, or 12, I don't know, depends on how you define this. And then you go to the next note, and then you turn it off. So, pretty much similar to MIDI note on and note off, but just that now we have instrument information. Well, I do have these. So, you can represent piano velocity 72, G1, but at the same time, you also have violin V80. So velocity 80, determine the dynamic, and playing G4 notes. There's another model called multi-track music machine, which is also a different way to think about. So this is the representation what it is. So you go from P start, track start, and this will be a whole lot of information. So you have like instrument 30, determine what the instrument is being used in this particular track. And then, you will have bar start. And then for each bar, you will have note on, note off, blah, blah, blah. So this is sort of like a very long representation of what the MIDI is. So this is exactly sort of like very similar to how MIDI actually store these information. But anyway, in general, what it looked like is something like this. So, you will flatten it into a long sequence. So you go from, the P start and go to the first track, and then go to the first bar, go over the first bar and go to the second bar. And, you will expand it with all the notes in that bar, and, end this bar, start the next bar, and then, expand it with all the notes you have, and until you have the whole track. And then you go back and then track end, start another track, and then do these things again and again. So, the end result is a super lengthy sequence of all the MIDI message, but you can do, multi-track music generation in some sense. Cool. And this is one of my past work, but this is multi-track music transformer. So sort of yet another way to do it. So you can also think about this like a compound word. But you have note-based representation rather than because I feel like MIDI message is kind of interesting because you are technically defining how to control the keyboard rather than generating the sheet music, understanding what each note play a role in the generation. So this is sort of like an alternative representation that's note-based. So each single line of these stuff represent a note. So the note is defined by where the beat is, where the position is, so where the timing is, what is the pitch, what is the duration, and what is the instrument being used. So, if you train it on this symbolic orchestral database, which is a more symphony or orchestral data set, this is something you can get. Cool. So if you look at these stuff, is basically each single row is a note itself rather than it's like MIDI on and off. And there are no time shift events. Why? Because if you just simply define where the beat is, where the position of that note is, then you don't necessarily need to define time shift, because you just go from one note to the other note and you define that position exactly by doing it. Anyway, but also you can look into drums. Drum is a bit different for MIDI because drum is a specific channel, which is channel 10. So sometimes, if you work on MIDI, then you will definitely realize that, channel 10 is just reserved for drums. But it's also encoded by the same MIDI pitch, which is very confusing. So, 30, each single different note for drum is corresponds to a certain drum pitch. So, acoustic bass drum, and, somewhere you have closed hi-hat, open hi-hat, and the snare. So 35, 38, 42, sort of the most important three drum notes in MIDI. And there's a tons of, models that support drums, MuseNet, Song from Pi, Triple M that we just look at, and many more. Cool. A big challenge of music generation, symbolic music generation, is just looking into how different, representation work for music generation. And it's not as simple as, natural language processing, where, basically you have few options on how you represent, like turn Wikipedia article into a sequence of numbers. For music generation is always not obvious. If you want to look into it, there are some dedicated library to get all these different representation that we talk about. And for symbolic music generation, these are some of the most commonly used data sets. So we have GSPOT Corel, where people started to look into what we can generate using all these machine learning models. So, Corel is just for part mostly, monophonic melodies. And we have MusicNet, which extended a bit. So now you have like string quartets and some other more complex ensembles, and you have the folk song data set, which is sort of like the one that similar to the folk RNN is trained on. And you also have more other data set, Wikiphonia, LAC MIDI data set, Meta MIDI. So these are, larger MIDI data set that just scraping the whole internet. And, nowadays people are not intensively using MIDI. So all these models sort of have a unique sound that, is like 20 or 30 years ago. So it's not the current music because, people, MIDI protocol is old, and nowadays people are not using MIDI quite often as you think about. Cool. So you can look into what these models are like. Some of them are larger than the other, and they have different genres. Some of them are just classical, say Maestro, but some of them are very, diverse data. Cool. Any question? What we just talked about? Yeah.
Are transformers with like music analysis, are they mostly used for the purpose of generation, or like as classification used?
Oh, you mean it's used everywhere?
Okay.
Yeah, so nowadays, pretty much whatever you can use as RNNs, you can use transformer as an alternative. So, I don't think Demox use it, but there are also one of the state-of-the-art classification model, audio classification model, not music classification model, is the something based on vision transformer. It's called, I forgot what it's called. Audio transformer or something. Yeah. Yeah. So there's, transformer being used there. And transcription is where also people intensively use transform model, because the original transform model is for machine translation. So, transcription is sort of like a translation going from, some, audio to the actual, sheet music. So you can view it as a sort of like a machine translation problem, but also OMR is sort of similar. If you slice the image and view it as, all the information, if you slice the input image as a sequence of, image patches, then you can sort of also frame it as a translation problem. And so it's also used there, and all different places. So not just for symbolic music. And you will also see audio case where people are also using transformer to generate.
Okay.
Yeah. So all these models, even though there are some paradigms how it's being used. So, think about the CNN thing. We talk about how we also explore in the homework that how it can be used in classification. But, what we are going to talk about next is that can we use CNN to generate music in Pianoroll format? So they can be also used in different places. And demux, you will see all the CNNs there. So the difference between the network architecture, so transformers, CNNs, RNNs, these are the the models, the network architecture, the neural network. But also looking at the framework, you have different framework. We talk about, transformer is an autoregressive model. And US like GAN, generative adversarial net, BAE, or latent diffusion model and diffusion model. Those are different framework to train these models, but the underlying network architecture can be reused different places. Yeah. Cool. Oh, good. Then we would just talk a little bit about Pianoroll-based music generation, which we are very behind the schedule. Anyway, cool. I would just keep this because we talk about these. So we were talking about transformers. Cool. Okay, cool. So, before we jump into it, we will first talk about a very interesting model called generative adversarial network. And then we will see how we can use this to generate, music in Pianoroll format. Or in the future, you will see people also use this to generate, audio or, spectrogram. So the first thing is we should talk about is discriminative versus generative models. So discriminative models are basically models we look at in the past, classification model, transcription model, blah, blah, blah model, that we are sort of like learning the decision boundary to see where the, the boundary is. For generative model, it's a little bit different in terms of machine learning perspective, where we are actually looking into how we can learn the underlying distribution. So that's a technical term, but essentially they're different in terms of the thing that you're learning. So PY given X, so the label given all the input information, rather, or you are doing the exact modeling of the distribution. So, we just talk about transformer, talk about LSTM, talk about ChatGPT-ish, that idea of autoregressive training, which is just generating the next word given all the past word, the word sequence. So that's a very interesting case where we are essentially modeling that, how do we generate the whole sentence. But at each single step, we are sort of doing discriminative model where we are just doing some sort of like, given all the past information, what's the most likely next word? So autoregressive model is something, has sort of like discriminative model in some sense to guess what the next word is in each single step. But as a whole, when you are generating a full sequence, it's just generating something from scratch, then it's a generative model. But anyway, for generative model, what we are doing, this is the paradigm of generative model, is that we are not just generating that distribution directly. Usually what we want to do is going from some random distribution to a data distribution. So if you are familiar with the, diffusion model, you always see people showing some, GIF that's going from a totally noisy image and then suddenly just become, some image that look nice. So that's sort of the paradigm that we are using mostly. So we are not generating the data distribution just out from nothing. Usually what we want to do is that we grab some, Gaussian or, whatever uniform distribution, and we want to use a neural network to turn it into some other data distribution. So, the key of generative adversarial network is that, ideally what we want to get is going from this random distribution to some, data distribution. So think about all these nodes are, these are just noisy images, and these are, the real images or, real music. What we want to do, initially, when you start using this model, initially it will be something that doesn't look like the data distribution that you have in the end. So essentially what we want to do here in generative adversarial network is to see how they differ. And we want to define a loss function so that you can gradually turn this, green bean-like stuff into another more bean-like stuff, more like the PX that you have. So, the essential key of deep learning is to find what the loss function is. But there's no easy way to measure the difference between these two different distributions. So, GN, under the hood, we will see later. But under the hood, what it wants to do is that, well, neural network is great. So what about we just use another neural network to do it? So let's dig into it. So generative adversarial network is was proposed in 2014. So usually people mark it as the start of the Gen AI, where people first time realize that we can potentially use these potentially initially dealt with as boring machine learning model to do some creative or interesting stuff to generate something cool. So what we have in GN is that we have a bunch of real samples. So think about a bunch of real music that we have, real MIDI files. And then what we want to do is to train some generator, which is a machine learning machine learning or a neural network that go from some random noise to some of the fake samples. So think about these two are, these are MIDI that generate, which, really bad at the beginning. And you also have some of the real good music examples. And what you want to do is to, grab or train another discriminator, which is another neural network, to look at whether they are real or fake. So, the discriminator aims to tell the fake samples from real samples. But at the same time, it's doing that, interesting gaming between them where the generator aims to make the fake samples indistinguishable from the real samples for the discriminator. These are the loss function technically, but what it wants to do is to see this adversary where the discriminator is trying to tell which are the bad examples, but at the same time the generator will improve based on the feedback coming back from the discriminator. So that's how GNN work. So you can think about it like in the case if you want to produce fake money, then this case the generator is just like initially you print something that doesn't look like anything real, and then there will be some examiner just looking at those things, and initially it's so easy to tell these are fake money, but over the time it will improve. So, you will generate more and more realistic fake images, fake music, or fake money, fake whatever. And, the examiner will also improve over time because, now things are harder to, to tell from one another. And at the end, it will sort of like reach an equilibrium where, we can no longer tell fake from real, but at the same time, the generator just do its best. Anyway, how you train it, we don't necessarily care about the discriminator, which is just the examiner. We typically don't care about it. So we would drop it and we just look at the generator, and now you have a bunch of random noise. Then you can just use it and then, grab some whatever random vector is, and then you just send it to the generator to get the output. So this was the original model, one of the early model that people use. But these are the real examples. So if you're using a convolutional GN, you wanted to generate image like this. And the model is just a CNN models that, unlike the one that we see in homework 2, going from a large a high resolution image to lower resolution image, but we do it the opposite way in the generator, which is called transposed convolution. But basically, you can use the same convolution neural network. Think about the stride, think about the filter size, and think about upsampling, but you can do some clever thing so that you can turn that convolution neural network the opposite way, that go from something very low resolution to higher resolution. So that's what the generator wants to do. Initially, it's just a random vector, but you gradually turn it into a larger, high resolution image. So this would be some of the, early GN generated room images. So as you can see, it's not perfect. So, GN at the beginning is just generating stuff like this. So you just use CNN for both the generator and discriminator. So the model at this point, the discriminator will just look at these fake images and the real images. And the discriminator doesn't know one from another, but it will be trained to sort of like mark all of these fake samples as fake and all the real sample as real. And with that feedback, you can actually train your generator so that you make all these fake samples in the next round more real for the discriminator. And that's how you play this, game theory thing where you are making a fake competition to improve. So, I don't know, think about writing in some sense, where you started writing something and then you will read it again and you realize something is really bad and then you improve it. So in that case, you are sort of like self-improving just by creating a pseudo examinator to look at the stuff that you generate and then use that as the feedback to improve your self. So that's how GN works. Cool. So we will talk a little bit about how GN can be used to generate piano rolls. So this is also one of my shameless self-promotion of my work. But these are the early stuff of GN to generate piano rolls. So initially is just generating these random stuff that doesn't make any sense. If you look at the base channel, it's much easier. Even as it's not step 0, technically it's step 1. So in one shot, the model just realized, well, for base, most likely is 0 because, it's monophonic. It's most likely 0. So even in one single step, the model originally just think base should be, less nodes than the other. But initially it will be very noisy. And then at step 700, now, you see where the generator starting to sort of like constrain into the pitch range. So bass will be much lower and piano, string, guitars, those are, more common range, usually in the range of piano. So, you can definitely see it. So very high or pitch are not frequently used. And for the drum, you can start to see some of the, patterns. Doesn't make much sense, just random patterns. But, for drum, it's just, certain drum notes because not all the pitch are being used. So at this point, you will see that, the discriminator should be doing something more. Looking at this doesn't look like any piano roll that you see. But now starting at step 700, now the model has to look into some of the other things. For this, you can just sum it up and, say, well, you have too many notes. But for this, just summing up doesn't work. You have to look into whether you have some structure, whether you have some chords that make any sense, or does it fit in the chords. So now going to, step 500, then you will see that the bass now is pretty good. It's, some monophonic notes that's, on the lower range. And then strings are generating chords that you can definitely see. But piano, guitar, nothing. Drum still having a hard time. But a lot of the time, it will just improve that, bass now become more steady, and you can see some of the drum notes that has the pattern and, stuff like that. So this is the sort of like, we trained it for much longer anyway, but you can definitely see how it evolves over time. Cool. And the generator improves over time. So does the discriminator. So that's sort of the idea of, GN. Cool. I think we are running out of time. But this sort of gives you a sense what we are doing next. We haven't talked about Pianoroll. Somehow I messed out on the the thing, but we could look into these next week. So we will talk about how you can use GN. So you just saw it, but you can use GN to generate music in Pianoroll format, but you can also use diffusion model. So that sort of give you the sense how we can use it to generate sheet music in a different format. Cool. See you next Monday. Oh, I didn't share the screen. Shit.
Wait, the whole lecture?
Yeah.
Oh.
I didn't see the message. Okay, anyway.